All right. So we're going to, over the course of the next few lectures, we're going to talk about some mathematics that you would encounter in politics. So we're going to talk about apportionment in the next couple of lectures, and then we'll talk about some voting issues in a couple of lectures as well. And then that'll be the end of the course. So anyway, let's get to it. So apportionment is about the distribution of representatives into appropriate shares. So, for example, how many representatives should each state have in the U.S. House of Representatives? At first glance, this seems like kind of an easy problem to solve, but as we'll see, it can be a little bit tricky. And the main issue is how we deal with a situation where the number of representatives is not a whole number. So for that, first of all, we need a definition. So in a decimal number, the digits to the left of the decimal are called the integer part of the number, and the numbers to the right of the decimal are called the fractional part of the number. So for example, the integer part of 4.23 is 4, right? It's the stuff that comes before the decimal. The decimal part of 4.23 is 0.23, right? It's the stuff that comes after the decimal. Okay, so when thinking about apportionment, a natural place to start is to give every group its appropriate integer part, number of representatives, and then if there are any seats left, give them to the groups with the largest decimal parts. And in fact, this is exactly the method that Alexander Hamilton proposed to apportion the first U.S. Congress. Okay, so here it is. In all of its glory, right? So the Hamilton apportionment method works like this. So let's say that our representatives sit on a governing board, right? So, you know, R could be like, this could be, for example, a House of Representatives where there are, let's say, 200 members of the House of Representatives, and so then R would be 200, okay? But it doesn't have to be a government thing, though. It could be like a business thing, you know, if you're sitting on some kind of governing board. But anyway, suppose that our representatives sit on a governing board meant to represent a population of N individuals. And suppose that group 1 in the population is made up of G1 individuals. Okay? So this could be, so tying this to like House of Representatives, for example. There's somewhere in the neighborhood of 300 million Americans, right? And we have, oh, this is embarrassing. I don't remember how many members of the House of Representatives currently we have. But, oh goodness, what is it? Let me pause and look it up. Let me pause the video and look it up real quick. 435. If you knew that, bonus points to you. Brownie points. Anyway, 435. Okay, so the U.S. House of Representatives has 435 seats, right? So R would be 435. The United States in total has about 300 million people, so N would be 300 million. And then if we wanted to figure out how many representatives California should have, then Group 1 would be California, and G1 would be the number of people that live in California, which I think is around 40 million. Okay, so that's what those symbols mean. Okay, so with all of that in mind, now here's how the Hamilton apportionment method works. So first, we're going to determine the exact number E1 of representatives due to Group 1. So it's the number of representatives that Group 1 deserves to have, right? And the way that we do that, the way we find that number is by performing the calculation E1 equals G1 divided by N times R. So let's break this down so that it makes a little bit more sense. So first of all, note that G1 divided by N, this would be the number of people in Group 1 divided by the total number of people in the population. So in other words, this would be the percentage of people in Group 1. This would be the percentage of people in Group 1. And the idea is that the percentage of people in Group 1 should equal the percentage of representatives that they get in the House of Representatives, or, you know, whatever other governing board you're talking about. right? So this is the percentage of representatives that they should have. You multiply that by the number of representatives available, and that should give you the exact number of representatives that group 1 should have. Okay? You're going to do the same thing for groups 2, 3, 4, and so forth. In the case of the U.S. House of Representatives, there would be 50 groups because you have 50 states. Okay? Okay, so now the problem, though, is this. So this is likely to be some kind of decimal number, right? So E1 might come out to 45.763, right? Well, you can't have 0.763 individuals, right? It doesn't make sense. So you would either have 45 or 46 individuals, right? That you would apportion to represent this first group in that case. So what we do is we assign the integer part of E1 to group 1. And then we assign the integer part of E2 to group 2 and so forth. Now, having done all of that, you might have a couple representatives left over to assign to some state, right? So again, there are 435 representatives in the U.S. House of Representatives. By the time you finish step 1 and step 2, maybe you've only assigned 432 of them. So you have 3 more representatives that you still need to assign to a state, right? That you still need to apportion or allocate to a state. So the way that you figure out which states they should go to is by looking at the decimal part of the number. So if there are more representatives left over, then the first additional representative goes to the group with the largest fractional part. The second additional representative, if any, goes to the group with the second largest fractional part, and so forth. And then you continue in this manner until you've assigned all additional representatives. So that's the Hamilton apportionment method. Hold on a sec. Okay, so that's the Hamilton apportionment method. Let's do an example. So this first example says 3 companies, A, B, and C, formed a consortium to develop wind energy off the coast of New England. The companies have agreed to form a 9-member board with representatives from the 3 companies to oversee the project. Each company will have at least 1 representative on the board, and additional board members will be assigned in proportion to the number of stockholders in each company. Company A has 4,700 stockholders, Company B has 3,700 stockholders, and Company C has 1,600 stockholders. Use the Hamilton apportionment method to allocate the 9 board members. Okay, hold on a sec. Okay, sorry about that. I keep getting interrupted. Okay, so let's use Hamilton's method here, or the Hamilton apportionment method. So here's how it works. I'm going to do this. I'm going to organize my work into a table. And so we have 3 companies. So I'm going to make a column for the company. And then we're going to do step 1. Which is the number of board members that each company deserves. So members deserved. Okay, and let's just do that, right? So for company A, B, and C. So for company A, Company A has 4,700 stockholders. How many stockholders are there in total? Well, we would need to add that up, right? So we would say 4,700 plus 3,700 plus 1,600 is 10,000, right? So the total number of the total population, this would be n in the formula that we gave earlier, right? So maybe I'll do this as kind of a scratch work up here. N is 4,700 plus 3,700 plus 1,600, and that comes out to 10,000. Okay, so for company A, we're going to have 4,700 out of 10,000. That's the percentage of representatives that company A should have, and then we're going to multiply that by the number of representatives, the number of representatives possible. All right, so that's 9. What do we get? Let's see, 4,700 out of 10,000 times 9. That comes out to 4.23. Okay, so company A deserves 4.23 members on the board. Well, obviously they're not going to have 4.23 members on the board, so we'll just assign 4 members on the board to represent company A. All right, company B should get 3,700 out of 10,000 times 9. And that comes out to 3.33. And then company C should get 1,600 out of 10,000 times 9. That comes out to 1.44. Okay, so step 2, we're going to assign integer parts. Okay, since it doesn't make sense to say, well, company A will have 4.23 representatives and company C will have 1.44 representatives, right? That doesn't make sense. So what we'll say instead is that company A is going to have 4 representatives, company B will have 3 representatives, and company C will have 1 representative. Okay. Now, to determine if we need to make any more assignments, we need to look at some totals, right? So the total number of members deserved would be 4.23 plus 3.33 plus 1.44, which comes out to exactly 9, right? Which is good. That's what we want, because there's supposed to be 9. It's supposed to be a 9-member board, right? But if you look at the number of representatives that we've actually assigned this way, we only have 4 plus 3 is 7 plus 1 is 8. So we still need to make one more assignment, right? We need to make one more assignment. So that's step 3. Assign additional member. And the question is, which of these companies deserves the extra representation? Well, obviously it would be the one that has the largest decimal part, right? And so that would be company C, right? Company C has the largest decimal part, right, of 0.44. So they deserve the additional member, right? So we're actually, our end product is going to be this. Company A will have 4 representatives, Company B will have 3 representatives, and Company C will have 2 representatives, and that makes for 9 representatives in total. So there's the representation, right? So we'll say Company A gets 4 representatives, Company B gets 3 representatives, and Company C gets 2 representatives. Okay, and that's the apportionment that we would get using the Hamilton apportionment method. Okay, now you may think, well, that's not all that tricky. I mean, maybe it's a little bit tedious, but once you see an example, it's really not that bad. And that's true, but see, problems occur, right? Problems occur when you apply this method. And to see why, let's take a look at the next example. It says, suppose the consortium from example 1 decides to increase the size of the board to 10 members. Right? So before they only had a 9-member board, now they're going to have a 10-member board. Let's use the Hamilton apportionment method to apportion the 10-member board. Okay, so I'm going to do the same thing and create a little chart. Okay, and notice that the numbers haven't changed. The number of stockholders is still the same for each group, right? So the total number of stockholders is still 10,000. The only thing that's changed is the number of board members, right? So this time we need to apportion 10 people instead of only apportioning 9. So for company A, it's going to be 4,700 out of 10,000 times 10. Right? Instead of multiplying by 9, we'll multiply by 10. And that comes out to 4.7. Okay, so this is step 1. For part B, it would be 3,700 out of 10,000 times 10. That would be 3.7. And then for company C, it would be 1,600 out of 10,000 times 10, and that comes out to 1.6. So if you add these up now, 7 plus 7 is 14, plus 6 is 20, so it's a 0, carry the 2, 7, 8, 9, 10. You would get 10, right? So you get 10, which is good, right? That's what we're aiming for. So this is just a way to check our work up here. But now step 2 is where we assign the integer parts. So company A is going to get 4 representatives, company B is going to get 3 representatives, and company C is going to get 1 representative. But notice that that comes out to just 8. So we need to assign some additional members. So step 3 is to assign some additional members, some additional representatives. So who's the most deserving? Well, notice that company A and company B both have the same decimal part. Fortunately for us, we have 2 more representatives to place. So we're going to give each of them an additional representative. So now company A will get 5 representatives, company B will get 4 representatives, and company C still just keeps 1 representative. If you add that up, that comes out to 10. So this time, the apportionment would look like this. Company A would have 5 representatives. Company B would have 4 representatives, and company C would have just 1 representative. And if you're comparing this with what we got for number 1, you'll notice hopefully the big issue here. And I apologize that I haven't been in full screen all that time. But anyway, you'll notice the big issue here was that in example 1, the board only had 9 members on it, but company C had 2 representatives on the board. Whereas in example 2, the number of board members went up to 10, and yet the number of representatives for company C went down 1, which is weird, right? It's just weird. It doesn't seem like if the board has more members on it that any of the companies should have a decrease in their number of representatives, right? That doesn't seem very fair. But that's something that can happen when you use that kind of naive sort of Hamilton approach. So note that in examples 1 and 2, company C had 2 representatives on the 9-member board, but only 1 representative on the 10-member board, even though the number of stockholders didn't change. A similar thing, and this has happened in history, right? So a similar thing happened in 1881 when the U.S. Congress found that Alabama was entitled to 8 representatives in a House having 299 members, but only 7 representatives in a House having 300 members, even though no state had a change in population. right? So it's weird that happens. But because this happened to Alabama in 1881, this strange kind of situation in which a group loses representation as the total number of representatives increases is called the Alabama paradox. And example 2 is a perfect illustration of an Alabama paradox. And by the way, this isn't the only time that this happened in American history. It happened again in 1890, right? Just a few years later. This time it happened to Arkansas. As the House increased from 359 to 360 members, Arkansas lost representation somehow, even though the population of the states hadn't really shifted all that much. So the reason the Alabama paradox occurred in example 2 was that when the board increased to 10, we reallocated the 9 board members from scratch, right? We completely redid the whole thing from scratch, which left open the possibility that, one of the companies could lose a representative. It doesn't feel right. It doesn't feel like that should happen. If the number of representatives increases, then no company should lose a representative, right? So in order to prevent this problem, we need a method so that once we allocate seats, they are never reallocated at a later date. Okay? This is not something that we're going to develop in this lecture, but we will develop it in a future lecture. However, we need to lay some groundwork, and that's what we'll be doing in the rest of this lecture, is laying some groundwork. So in order to make assignments on a once-and-done basis, we need a clear measure of who is most deserving of the next representative at each stage in the apportionment process. So one way that we do this, or one kind of piece of the puzzle, is to look at the average constituency of a state. So the average constituency of a state is the quotient population of the state divided by number of representatives from the state. And that makes sense, right? Like, let's say, just to make the numbers easy, let's say that the state has 10 people in it, and that there are 2 representatives from that state. Then it makes sense to say that each representative represents, on average, 10 divided by 2 equals 5. So each representative represents, on average, 5 people. Of course, it's much more complicated than that when you're dealing with a constituency of millions and millions of people, right? And you've got dozens of representatives like we do in California. But anyway, this is how you do it. Population of state divided by number of representatives from the state. Comparing the representation of 2 states A and B, we would say that A is more poorly represented than state B if the average constituency of A is greater than the average constituency of B. Right? In other words, if you perform this calculation for state A and you get 32, and then you perform this calculation for state B and you get 28, then that means that the representatives in state A have to represent 32 people on average, whereas the representatives in state B only have to represent 28 people on average, so that state B is better represented. Or in other words, state A is more poorly represented than state B. Okay? So let's do an example with some actual numbers. Following the 2010 census, the U.S. House of Representatives was reapportioned, and California, with a population of 37,341,989, was assigned 53 representatives. Florida, with a population of 18,900,773, was given 27 representatives. Right? Calculate the average constituency for each state to determine which state is more poorly represented. Okay. So for California, the population of the state was 37,341,989, and the number of representatives was 53. So let's see. 37,341,989 divided by 53 is about, so it's about 704,565, 0.8. right? I'll go a couple decimal places and say 0.83. So that's the average constituency for California. What about for Florida? For Florida, population was 18,900,773, and the number of representatives from Florida was 27. So 18,900,773 divided by 27 is about 700,028.63-ish. Okay. So their average constituency is actually pretty close, but because the average constituency for California is greater than the average constituency for Florida, we would say that California is more poorly represented, right? Each representative from California has to represent about 4,000 more people than each representative in Florida does. So we're less represented here in California than people in Florida. Or at least that was the case in 2010. So there are the average these are the average constituencies. And then as far as which state is more poorly represented, we would say California is more poorly represented. Okay. Now, it would be ideal to have an apportionment in which the average constituencies are the same for all states. However, that's usually not possible. But still, if we can't have equality, then we should try assigning the representatives to make the average constituencies as equal as possible, right? So even if we can't get perfect equality, we still want to be as equal as possible in terms of the average constituencies of the states. So one measure of how close we come to this goal is given below. So suppose that representatives are apportioned between two states, A and B. We define the absolute unfairness of this apportionment as the difference between the larger average constituency and the smaller one. So in other words, if state A has the larger average constituency, then the absolute unfairness would be the average constituency of A minus the average constituency of B. And notice that we always subtract the smaller one from the larger one so that the absolute unfairness is always a positive number. I guess you don't really have to worry about which one is bigger or smaller as long as you take the absolute value in the end. So if you subtract them and then take the absolute value of the difference, then you're good to go. And you don't have to worry necessarily about the order of the subtraction. But anyway, let's give an example of this. So number 4 here says, suppose the Weavers Guild with 1,542 members has 6 delegates on the National Arts Commission, and the Artists Alliance with 1,445 members has 5 delegates. Calculate the absolute unfairness for this assignment of delegates. Okay. Well, in order to calculate the absolute unfairness, first we need the average constituency of each of the groups. So let's do that for the Weavers Guild. The Weavers Guild has an average consistency of 1,542 divided by 6, because they had 6 delegates, right? So that's 257, exactly. Okay, the Artists Alliance, I put the apostrophe in the wrong place, it's the Weavers. So multiple weavers. Anyway, same way with the artists, right? Multiple artists. So their alliance would have 1,445 members and 5 delegates. So that's an average constituency of 289. Okay. So finally, the absolute unfairness is going to be 289 minus 257. So 289 minus 257 is 32. Okay, so there's the absolute unfairness. Okay. Last concept in this lecture is about the relative unfairness. So we're going to talk about the relative unfairness because the absolute unfairness is actually not a great way to compare the imbalance of apportionment between, or it's not a good way to compare the fairness of two different apportionments. Okay, so in other words, the absolute unfairness, which we just looked at, gives us a way to measure the imbalance of apportionment between two groups within the same apportionment. So calculating the absolute unfairness here and seeing that it's 32, that gives us a good measurement for how imbalanced this apportionment is, right? How imbalanced the groups within this apportionment is. But let's say that we wanted to compare how imbalanced this apportionment is versus this apportionment in example 3. Well, if you just looked at the absolute unfairness. So if you just looked at the absolute I don't know why I couldn't think of that word, but if you just looked at the absolute unfairness, and we weren't asked to do that in this particular example, but if you wanted to compare the absolute unfairness, you would say, well, it would be 704,565.83 minus 700,028.63. So 704,565.83 minus 700,028.63. That comes out to 4,537.2. And so you might look at that and you might think, okay, so the absolute unfairness here is 4,500. It's over 4,500, whereas the absolute unfairness here is just 32. And based on that, you might walk away with the assumption that this is a better apportionment for this set of circumstances than this apportionment is for this set of circumstances. But you'd be wrong. You'd be wrong to make that assessment. Why? Because here you're dealing with populations that are so much bigger, right? 4,500 in comparison with the 37 million and the 18 million that we were starting with is actually not that much, right? Whereas an absolute unfairness of 32, when we were only dealing with average constituencies of 257 and 289 to begin with, that's actually a much bigger deal. To see exactly how big it is, we would look at the relative unfairness. Okay. Here I'm just saying exactly what I said before, right? So in example 3, the absolute unfairness was 4,537, which is relatively small considering the size of the constituencies for California and Florida. In example 4, on the other hand, the absolute unfairness was 32, which is relatively large when we compare it to the average constituencies of 289 and 257. However, if we just compared the absolute unfairness in those examples, it would seem like the apportionment in example 3 is much more unfair than the apportionment in example 4, and that's just not true. right? So to compare apples to apples, we need to compare the relative unfairness, not the absolute unfairness. And here's how we do that. So when apportioning the representatives for two states, we define the relative unfairness of the apportionment as relative unfairness equals absolute unfairness divided by the smaller of the average constituency of the two states. I think that should say constituencies, but you get the idea. So for example, let's compute the relative unfairness for the apportionment of representatives to California and Florida in example 3, and the apportionment of delegates for the Weavers Guild and Artists Alliance in example 4. Okay. So for the for the example 3, right? This was the California-Florida example. The absolute unfairness was about 4,537. And the average consistency we'll say the average constituency. I'm having a hard time saying that word. Constituency. The average constituency for California was 704,565.83. And for Florida, the average constituency was 700,028.63. So the relative unfairness is the absolute unfairness, 4,537, divided by the smaller of the average constituencies. So that would be the 700, right? Because this one's smaller. This is the smaller or average constituency. Okay, so we're going to divide by 700,028.63. And what does that come out to? So 4,537 divided by 700,028.63 comes out to about 0.0065, we'll say. So we'll go 4 decimal places. Okay. For example 4, this would be the Weavers Guild and Artists Alliance. Weavers Guild and Artists Alliance. The absolute unfairness was 32. For the Weavers Guild, the average constituency was 257. And for the Artists Alliance, the average constituency was 289. Okay, so this one is the smaller average constituency. So the relative unfairness would be 32 divided by 257. Which is about 0.1245. Okay. So as you can see, even though the absolute unfairness in example 3 was much more than the absolute unfairness in example 4, when you compare their relative unfairness, you can see that actually the apportionment in example 3 is much more fair than the apportionment in example 4, right? So this apportionment is much more unfair, unequal. Okay, and that's all I have to say for now on the issue of apportionment.